Alright, so today we're going to be covering the topic of exponents, their rules, and the exponential functions, the characteristic example of that being e to the x, being the most well-renowned exponential function. Okay, but let's start here on the left side with the exponent rules, because they're kind of essential to our understanding, okay? So there's a series of identities and rules that go along with this. The first one being if I have something that has base a, and that base a is raised to an exponent, let's call that exponent x, then if I multiply that by something else with base a that has a different exponent, let's call that exponent y, then this can be rewritten as the form a as the base to the exponent x plus y. Okay? Consequently, if you start with something in the form a to the x plus y, it can go backwards. It can be rewritten as a to the x multiplied by a to the y. Okay? Now, let's go on to the next one, which is kind of the inverse of what we just covered. If I have some base a raised to an exponent x, and I divide that by base a to the exponent y, then that can be rewritten as base a to the exponent x minus y. So notice here that your order matters. A to the x divided by a to the y is not the same as a to the y divided by a to the x. So your exponent reflects that, because subtraction and division are not commutative. The next identity we're going to go over is if I have a to the x and I have this whole thing raised to the y, then this can be rewritten as a to the x times y. And if these are getting a bit hard to remember right now, don't anyone worry just one bit, because we're going to be going over how to understand these conceptually and how them make sense intuitively, so that you don't even remember them. You can just make sense of them on the spot. But we're going to go over that after we go through everything else. Okay? The next one we're going to go over is if I have a times b, and those are multiplied together and then raised to the exponent n, then I can use the distributive property and say that this is equal to a to the n multiplied by b to the n. And the same distributive property is allowed when I have a over b, all raised to the n. That can be rewritten as a to the n divided by b to the n. Then after that, we have the identity that I can't explain to you, you're just going to have to memorize outright. A to the 0 equals 1. Pretty simple, pretty straightforward, doesn't make conceptual sense, we're just going to have to remember it. Okay? Moving on from there, we have a to the negative exponent n, is equal to 1 over a to the n. Okay? And our final exponential identity that we're going to need to be aware of is if I have a and I raise it to some exponent n over n, then that is going to be equal to a raised to the m with a radical of base n. Okay? So let's start going through these and making them intuitive. Okay? If I have a squared times a to the third, then that equals a times a times a times a times a. And you'll notice here that this is 5 a's being multiplied together, which therefore makes it equal to a to the fifth. 5 is equal to 2 plus 3, as we have just seen demonstrated. Okay? Next identity, a squared divided by a to the first equals a times a over a. Okay? That is therefore equal to a to the first power. Okay? So 2 minus 1 equals 1, as you have now seen demonstrated. Next, we're going to look at, let's say, a squared quantity squared. And if I have a squared, that is a times a. And if I continue with my squared exponent, that is equal to a times a multiplied by a times a. And you see, this is now equal to a to the fourth. So you'll see that if my inner exponent is 2 and my outer exponent is 2, I multiply them together, and that produces the 4. If, let's say, I am dealing with ab squared, then that is equal to a times b multiplied by a times b, which can be rewritten as a times a multiplied b times b, which is equal to a squared times b squared. If, let's say, I have a over b squared, that's going to equal a over b times a over b, which is equal to a squared over b squared. You see? Distributes very nicely. So there's something I want to show you guys about this particular rule that may not be immediately intuitive. If I am given 1 over a to the negative n, that's going to equal 1 over a to the n. Okay? So I can do keep change flip on this. So this is equal to 1 divided by 1 over a to the n, which is equal to keep change flip 1 times a to the n. So 1 over a to the negative n therefore becomes a to the n. 2 over a to the negative n becomes 2a to the n. This negative n just puts it on the other side of the division bar. That's all it does, okay? Next, we're going to look at the exponential functions and how they behave. First, we're going to consider the standard case, f of x equals e to the x, and that has the shape like this, okay? So I would say that there are 2 points that are easy to evaluate for us, because e is an irrational number, 2.71 something something something, but in that irrationality, there are 2 numbers that we can deduce easily, and that occurs when x equals 0 and when x equals 1. Okay, when x equals 0, e to the 0, by this identity that we have demonstrated for you right here, any number to the 0 equals 1, which means whenever x equals 0, at this particular point right here, f of x equals 1. And from there, the only other number that's easy is e to the 1 equals e. So when x equals 1 here, we know that this number is going to be e. And the behavior of the function makes general sense. If I have e raised to the 0 power, that's going to give me exactly 1. Okay, so that gives me this number right here. If I have e raised to any power greater than 0, then it's going to give me a number greater than 1. If I raise e to any power less than 0, it's going to give me something less than 1. The only number that this doesn't work with is 1 to the x, because 1 squared equals 1 times 1 equals 1. So if I were to graph a graph of 1 to the x, it would just be a horizontal line at y equals 1. Okay? But back to the general scenario we're going through here. So when x is something less than 0, then we're looking at e to the negative something. Okay? We're looking at e 1 over e to the something. So 1 divided by something, it makes sense that this would be something less than 1. However, we should also notice that this function is never negative. It never exists in the bottom 2 quadrants. Why is that? Because you can never multiply a positive number by itself and get a negative number. That can't happen. Okay? 2 times 2 will never be negative 4. Now, if I wanted to flip it around and I wanted to make it negative, it would be negative all the time, as I will draw for you right now. If I were to graph f of x equals negative e to the x, it would look a little something like that. Okay? So I want to now help us understand what the graph might look like if we graphed f of x equals e to the negative x. That would put 1 over e to the a on the right side and e to the a on the left side, which means we would grow exponentially higher on the left and then go very, very tiny on the right. So what we did is we basically took the graph of f of x equals e to the x and we rotated it around the y-axis, 180 degrees. But we're going to get into a lot more of that manipulation of functions when we get into the transformations video. And that should be coming very shortly if it isn't up already. Thank you guys for watching. If you need any help, please reach out. Enjoy life.